Thank you very much, Rahul, for the introduction, for the opportunity to present our work here, and to Janek and Konrad for the invitation to be the visitor here in Warsaw for this 2 months. So this is my second seminar here in Warsaw about quantum repeaters. Around 1.5 years ago, I talked about the work in Delft on proof of principle repeaters, so that were based on near-term goals. And here we will discuss in this work in the group of Liang Zhang, we look more at the kind of more long-term goals of repeaters that are based on error corrections. And so this is a joint work with Kongju Shan and Liang Zhang at the University of Chicago, and Saikat Guha, who is at the University of Arizona. So I will start with a motivation that is exactly the same as 1.5 years ago, which is that if we want to perform quantum communication, then the transmissivity of the optical fiber decays exponentially with distance. So L0 would be some attenuation length of the fiber, and L would be some distance. And so the probability that we can transmit photons through such a fiber will decay exponentially. And we know that this also means that if we want to, for example, perform quantum key distribution through such a channel, then the rate of generating secret key, or the number of secret bits that we can generate per number of uses of the channel, will necessarily also decay exponentially with distance. And so the goal of quantum repeaters is to basically overcome these limitations. So in this talk, I will firstly provide a brief introduction to these quantum repeaters and what type of quantum repeaters on this very high level one considers. So I will contrast a little bit these repeaters based on this heralded entanglement generation and the repeaters based on error correction. And then this introduction to repeaters based on error correction will be a motivation for our repeater scheme that is based on GKP, Gottesman-Preskill codes that I will introduce. And then we'll describe how we can construct a simple repeater architecture from such GKP encoded qubits. Later, I will introduce how we can actually concatenate this GKP code with another code, and then provide this details of this more advanced repeater architecture that involves this concatenation of two types of codes. So GKP codes will be a bosonic continuous variable codes, and then we will concatenate them with some small discrete variable qubit code. But let's firstly start with this basic introduction to quantum repeaters. So the most standard type of quantum repeaters that we know and that exist in the literature for the very long time are based on heralded entanglement generation. And these already have been proposed by Hans Briegel in 1998 and coworkers. And this scheme is basically based on the idea that we can divide the whole communication distance into multiple elementary segments, elementary links. And so do you see my mouse?
Yes.
Okay, so this basically we divide this whole segment between 1 and 5 into this elementary links between 1, 2, 2, 3, 3, 4, and 4, 5. And then independently, over these links, one attempts to generate this short entangled links. And this generation process is probabilistic, but thanks to the fact that we have quantum memories at all these nodes, we can now independently try to generate all these links, and this significantly speeds up the process. And after a certain time where we already can confirm that all these short links have been generated, we can perform Bell measurement or entanglement swapping to connect all these links into one long distance link, where in order to know which Bell state we have effectively generated, we need to keep track of the outcomes of this Bell measurement. So this will be effectively 2 bits, and that need to be tracked and sent to the end nodes. And using this information, the end nodes can recover a desired entangled state. In practice, of course, performing all these operations at these repeater nodes will add noise. So the operations, this entanglement swapping operation will be noisy. And also, if we connect some non-perfect entangled links, we will end up with long-distance links that are also significantly decayed quality. So a solution to that is entanglement distillation, which means that whenever one establishes a link, one actually generates a large number of such links that would be only partially entangled because of noise in all the generation processes. And then we will perform local operations on both sides in order to distill a smaller number, or let's say one very highly entangled link. And because all these operations are noisy, we don't want to perform all this entanglement swapping everywhere at once, but we will only perform it in some kind of concatenated fashion where we perform the swapping operation after we have all the links only every second node. So for example, only in 1 and 3, and establishing links that are twice longer than the elementary links. And then we again generate large number of such links and try to distill a high quality link of this length 2. And then we follow the same procedure to establish link of length 4 and until we get all the way between Alice and Bob. And so this type of procedure, it's known that it's not difficult to establish that it will have that the time that we need to wait in order for Alice and Bob to have a long distance link will scale polynomially with the total communication distance, which is quite nice. So we overcome the exponential scaling of the that we have for direct transmission, but we will be limited by this classical communication between the end nodes. So because we have this entanglement distillation procedure to improve the quality of the state, and this procedure is probabilistic, so with some probability it succeeds, and with some probability it fails and we need to throw away the state. Because these operations are performed kind of in parallel across different segments, there needs to be constantly all the nodes need to communicate and send classical information between each other, whether the distillation in their nodes has succeeded or failed. Maybe this entanglement swapping operation is also probabilistic, in which case one also needs to communicate information whether the swapping succeeded or not. And in practice, this means that one always needs to wait for all this information. And for example, the memories of Alice and Bob needs to be able to store the quantum state all the way through all these levels until the last step, which means that if we want to scale up the scheme, we need to have basically quantum memories which will be able to maintain this quality of the state for so long. And so I believe that this kind of architecture will be the architecture on which first proof of principle repeaters will be built, but then we have this problem of scaling it to large distances due to this communication requirement and consequently the memory requirement. So one of the kind of solutions to that is to, instead of use this heralded entanglement generation, to focus on error correction instead. And so this type of error correction based architecture is more similar to what one can imagine in classical communication, where like how classical amplifiers work, in the sense that basically Alice or the sender would encode a logical qubit in large number of physical qubits in such a code such that when this state encoded in large number of qubits, or in this case photons, will be loss tolerant. So even though we lose some of the photons here in the fiber, the next repeater should be able to correct these losses and reconstruct the state even if some of the photons got lost. And then after that, it forwards it to the next repeater. So here we see that there is only one-way communication. The states are only sent from repeater 1 to repeater 2, from repeater 2 to repeater 3, and so on. And therefore, there is no problem that, for example, this node needs to wait for some information, some classical information to come from somewhere else in order to decide what to do. It just locally corrects what it receives and sends it further. And so like a simple way to how we would maybe try to quantify the resources needed for such a scheme is we would ask ourselves the question, if we want to be able to successfully send a quantum state from repeater 1 to, let's say, the last repeater, and we want to say that we want to do it with some fixed probability or near deterministically. So let's say with probability 99%, we want this state to be able to successfully arrive at the end. then what is the number of physical qubits that we need per logical qubit in order to achieve that? And from property of many of the codes that one considers, we can say that the number of these physical qubits per logical qubits needed is some function of the transmissivity of the elementary link, and then some polylogarithmic function of 1 over the effective error that we want to tolerate over the elementary link. So this epsilon effective is the probability of failure, the desired probability of failure over a single elementary link. So let's say, of course, if we want this probability to be as small as possible, then we will need a much larger number of physical qubits Q for a given, say, loss in the channel given transmissivity P0. And then we can re-express this epsilon effective in terms of the desired probability of success over the whole link. So P-sac would be some kind of desired probability that we want over the whole link, and then we take the square root over the number of stations to basically reflect this quantity that corresponds to a single elementary link. And this function has effectively now, if we want to look at the scaling of this function of Q as a function of a number of stations, so which would correspond to our length, for a fixed P0, so a regular spacing of the repeaters, and for a fixed probability of success that we determine, effectively this function has a nice logarithmic scaling with respect to the number of stations. So this seems a very promising architecture with that respect, with a nice scaling and no need to require this additional communication. But even though, if let's say consider some kind of practical scenarios, so if let's say that in our channel we will optimize the repeater positioning, and we also say that there is a 10% coupling losses, so there is a 10% of losing the photons just when transferring it from a repeater to a fiber. Then if we want to achieve communication with the considered architecture in this paper with parity codes, then we need to entangle 100 qubits, let's say 100 photons, into a single logical qubit in order to communicate over 1,000 kilometers. And if we want to consider 10,000 kilometers, then more than 200. So what this means is that actually this is quite challenging, because let's say in the channel we need to have 100 photons entangled, but then in a repeater, one way of performing this error correction would be to put all this, say 100 or 200 photons into 200 memories, still maintaining all the entanglement between all the photons, and then do operations on these qubits in such a way as to be able to correct the errors and not destroy the entanglement. So this seems very challenging, especially if we want to consider near-term goals. So the goal of this project is to see whether we can reduce this Q by saying that we will not consider physical qubits as, let's say, photons, but each of these qubits will actually already be encoded in a GKP code that I will discuss now. So basically, we want to reduce the number of qubits by having each of the qubits encoded in some other code that will protect us against losses. And then we will have 2 levels of encoding, because on one level we have these GKP qubits, that multiple of which we will entangle together on some second level to have this overall protection against losses. And then the goal is to show that if we use this GKP qubit, then on the second level we will not need this Q as large as this 100 or 200, but much less. So now I will provide an introduction what is the GKP code. So GKP code is stands for Gottesman, Kitaev, and Pritzker. This is a code that was already proposed a long time ago, and is based on an interesting observation that though we cannot measure position and momentum simultaneously, we can define 2 operators as Q and as P, for which are effectively periodic functions of Q and P. And actually, these 2 operators, they do commute. So such operations that are periodic functions of Q and P effectively allow us to measure Q and P in a periodic fashion. So specifically, these two operators allow us to measure Q and P simultaneously modulo root pi. And so that means that we can define a common eigenspace of these two operators. And in particular, the common eigenspace with eigenvalue 1 will correspond to our GKP code. And what would such code words look like? So for example, a logical 0 will be defined as the superposition of position eigenstates that are periodically spaced every 2 root pi, while logical 1 will be defined the same way, but now shifted by root pi with respect to 0. So that we can also see on this picture that 0 would be that we will have a 0 that is a superposition of this periodically spaced eigenstates in Q quadrature, and the same for 1, but 1 is shifted by half of the period with respect to 0. So these two states are orthogonal. And the same we can define for the x basis. It turns out that it will be a corresponding superposition of P quadrature. And so now if we want to visualize what this kind of states look like, so here we show a Wigner function of such a GKP code state. And so we see that this would correspond to a periodic grid structure in phase space, which where the state is actually highly non-classical. So these blue regions describe the Wigner function negativity. And so we see that in order to prepare such states, we will need a little bit more than just a Gaussian operation. So, the state is definitely a very non-trivial resource, but as we will see, it has a lot of very desirable properties.
So Filip, can I ask you something?
Mm-hmm.
So you just consider these two logical states here, yes? So why don't you try more states? I mean, is it not helpful to consider more states in this space?
Also, just a basis, right? So I just describe. So basically, here we consider a qubit encoding. So we design a spacing in such a way that basically, or we define the states in such a way that we only consider effectively that we only obtain a two-dimensional space. So this here I just described two states that can form a basis, but of course every superposition of these two states, or say these two states, will also be in the +1 eigenspace of these two operators.
Okay.
So, but of course, but what one can do is one can define this spacings so differently, such that one would be able to define a 3-dimension like a qtrit or a quadrit in that space. But as we will see, because somehow I can think because of the uncertainty principle, somehow if we want to define a higher dimensional state, then we will have less resilience to noise, because somehow what we want to do is we have this grid state, and then a small displacement. The small displacement of this grid state will take us away from the +1 eigenspace of these operators. So we will be able to correct some displacement, detect some small displacements that are less than this period, and then bring it back to this logical space. But if we start defining now higher dimensional objects, we can maybe store more information, but we will be able to correct less shifts. So there will be somehow a trade-off with that respect. And does that answer the question?
Yes. This was exactly what I wanted to know. Thanks.
Mm-hmm. Okay, so now I will describe what type of errors and how we will correct these errors. So we can visualize this this GKP state as basically this, for these two specific operators. This will correspond to a square lattice GKP code, where let's say that now effectively what we have for such a perfect code would be that we would have Dirac delta functions at these locations marked with dots, and then the squares mark effectively the correctable regions. So what I mean here is that now let's say that we had some noise, that some displacement, random displacement noise that shifted this grid such that this black dot is going to shift from here to this to this green green cross, like this. So now this would cause an error, but basically what happens is by measuring the stabilizers, we can find out that this grid, that the whole grid effectively has shifted, and then we can bring that state from this shifted location back to the original one. So the small shifts within that square can actually be detected by measuring the stabilizers and correct it. But now we have what happens if we have very large shifts. So that we will see now here. So let's say that again this this black peak from here was actually now shifted all the way to here, like this. So this was a very much larger shift. And now if we want to consider what happens when we do error correction, is that, well, the error correction would, so of course, if this cross from here this peak from here moved here, then actually this lower peak will move here because the whole grid structure that moves. So now we will think that actually this cross was corresponding to this peak, or analogously, we will think that this cross that was corresponding to this peak centered here, we will now only correct it back to here. So that means that effectively the whole grid will shift by, in this case, by square root of pi, which will correspond to a logical Pauli Z error in such an encoding. So if we consider kind of what kind of errors we have, basically, if we have a root pi shift along the p quadrature, that corresponds to an application of a logical Pauli Z operation. If we do that along the q quadrature, that corresponds to a logical x flip. And if we have a shift by root pi along two quadratures, that will be logical y flips. So I have described how we can use such a code in order to correct this random shift errors. But of course, if we want to talk about communication, we actually don't have this kind of random shift errors, but we have energy attenuation, or a pure loss channel. So I described how to deal with this random displacement error. But the pure loss channel will not cause a random displacement. So here it's illustrated on a, say, coherent state that is randomly displaced around this central point. But for the pure loss channel, we will have some coherent state, let's say, that will be basically attenuated. So it will be brought back to the origin. So this is a very different type of noise. And we said that the GKP code is it enables us to correct this random shift. But fortunately, it has been found that there is a very nice strategy of effectively combining this loss channel with phases insensitive amplification that effectively results in such a random displacement. So if I have loss, I will have my state will shift towards the origin, but now I can apply amplification to kind of bring the state back in the original direction. But of course, amplification will contribute noise, because otherwise it would violate no cloning theorem. And so this noise added by the amplification will effectively result in this, as if we had the original state that was randomly displaced along its original location. And then basically after that, we can use the GKP encoding to correct such an error. So in practice, what this means is that we could prepare a GKP state, send it through a lossy channel, then apply amplification by the amount of amplification is inversely proportional to the amount of loss that we had in the channel. And effectively, then we will end up with this random displacement that we can use the GKP code to correct this resulting error that now came from this amplification noise, basically. So of course, I talked here about this GKP state as a infinite size grid or infinite grid structure, where all the peaks are basically delta functions. So of course, that's unphysical. That would require infinite amount of energy. So in practice, the quality of such a state can be quantified by its squeezing, or which would correspond to the fact that actually we will not have an infinite size grid, but we will have some grid with some kind of Gaussian overlying envelope, such that for large distances away from the origin, the probability amplitude of the peak will decay to 0. And at the same time, each of the individual peaks will now not be a delta function, but will be some kind of Gaussian peak with some standard deviation sigma GKP. And actually, we can quantify this by basically this corresponds to the amount of squeezing that we need to, GKP squeezing that we input in such a state. And we can quantify it by the squeezing parameter, where here inside the logarithm, we basically compare the variance of our GKP peaks to effectively the variance of a coherent state. And so in our repeater model, we will investigate how much such GKP squeezing we need in order to achieve long distance quantum communication. Okay, so this was the introduction to the GKP code, and now I will provide describe how we can basically construct a simple repeater chain, so a linear repeater network that uses such GKP encoding. And so here the picture is kind of rather simple. What we will do is we will prepare our encoded state. We will send it through the channel, apply this phase insensitive amplification, and then they perform this GKP correction in a Q and P quadrature and send it through the next channel and so on. So basically here we take a single qubit, we encode it in a single GKP mode, and then send it through such channel where every repeater performs this GKP correction in Q and P quadratures, where each correction basically corresponds to, so GKP correction in Q would corresponds to measuring a skew stabilizer and then applying a correction shift based on this measured stabilizer value, and then we will do the same for the P quadrature and send it to the next repeater.
Philip, can I interrupt you? I think Janek has some question.
Yes, I thought of asking it now because you start talking about repeaters. So I wanted to ask about the GKP code. So because you mentioned it's in the formalism of stabilizers, so I was thinking of standard quantum error correction, think what is the stabilizer for that code, in the sense you have these S operators that you introduced in the beginning. Can I explicitly see what is the stabilizer? And just maybe it's a trivial question, but so for you it was natural, the stabilizers are the shifts, no? And then you have the gates, but mathematically, I mean, I should form some kind of a group, I understand, no?
Right. So here, okay. So now, of course, these two stabilizers, they don't take. So in a qubit code, they only take. I have eigenvalues +1 or -1.
And then I form the code on the +1.
Right. Right. But here somehow the whole space is infinite dimensional. But because the stabilizers don't take only eigenvalues +1 or -1, but they can take continuous values, and this is actually the syndromes that we measure. So the syndromes that we measure are some continuous numbers, where basically if you have, let's say you have the eigenvalue +1, you are in the code space, and then any kind of number that is away from +1 will be some kind of shift away from this.
Okay, and this is what you call shift then. Okay.
Yes.
Okay, thank you.
Yeah, so you can think that you either measure the stabilizers and then they give you some of these complex numbers, or you can think that basically you measure position and momentum, in this case modulo root pi, and so Q and P can be any value between -√pi over, so basically you can measure any value between -√pi over 2 to +√pi over 2, and if that value is 0, that is your code space basically.
Okay, thank you.
Okay. So yes, so we got to this simple repeater architecture, and so yes, so what of course what we want to overcome is the losses in the channel. So in the channel there would be some transmissivity that will be a product of, so eta 0 is some kind of photon coupling efficiency, meaning how much photons we are able to successfully, the fraction of the photons that we can successfully transfer from fiber to the repeater and from the repeater into the fiber. And then we have this exponential decay with distance over such an elementary link, and L0 is some attenuation length of the channel. And if we assume that we can perform all these operations at the telecommunication wavelength, then the typically considered telecom channel attenuation would be around 22 kilometers. And additionally, we assume, so in order to measure this SQ and SP stabilizers, we will actually need to have some ancilla GKP modes. So basically, we would need to transfer the information from a data mode onto a GKP ancilla mode, and then measuring this GKP ancilla mode will enable us to obtain the stabilizer outcome. And so we will consider that these ancillas that we use for the stabilizer measurement are, of course, not perfect. They have some finite amount of squeezing that we will quantify by the sigma GKP. And the simple now the analysis how to place the repeaters would be based on the ideas that, well, if we have too few repeaters, then this exponential decay e to the minus L will cause too much loss. But if we have too many repeaters placed too nearby to each other, then if this eta 0 is not perfect, then we will basically have too much loss from this coupling efficiency. So we would want to optimize this repeater positioning. So we will come back to the results of this optimization later, because now I want to introduce this notion of how we can concatenate this GKP code with now a higher level qubit code. And so this is very much related to what Janek has just asked. So the syndromes that we measure are actually continuous, provide us continuous analog information. So this is not some kind of discrete number that is plus or minus 1. And we will see now that this information can actually be very useful in ways that we cannot use the syndrome in a qubit code. So let's say, for example, that we had a GKP code which had a peak at exactly 0. So if there was no noise at 0, there should be a delta peak. And then it went through some channel that had some Gaussian, that sampled random shifts from a Gaussian distribution. So this Gaussian distribution is drawn here. And then we measured this syndrome. And then we find that we measured the value somewhere here. So now the crucial thing is that we can effectively, because we can only measure the syndrome is only this periodic information, the outcome of our syndrome measurements can only lie in the interval minus root pi over 2 to root pi over 2. So if we measure the value here, the real shift could be either from 0 to here, or it could have been all the way from 0 to here, or all the way from 0 to here. But what we will, of course, do is we will shift it back to 0, because then this is the kind of the most likely state. So because we have this kind of Gaussian noise structure, the probability that we had a shift that was so large as going from 0 to here is very small comparing to this tiny shift here. So we will just apply a small displacement to bring the small displacement by this small amount to the left. And so not only do we have this kind of procedure that tells us that if we measure a given syndrome, we shift it back by the minus the value of that syndrome, but we also have a way to quantify how reliable is our error correction. So in this case, if the shift was small, we see that the reliability of our step of shifting it back to by the small amount here is quite high, because the probability of these other errors would be negligible. But now, if we measure something very close to this boundary, then, and of course, what we are again going to do is we are going to perform something that we are going to correct the most likely error, which is shifting this arrow back to 0, so shifting it to the left. But of course, other possible errors that would not be correctable would be a shift all the way to here, or shift to the left to here. So all these three errors will map after the syndrome measurement to this value. And now we see that the height of this arrow is maybe not that much larger than the height of this arrow. So although we will shift it back to here, we already have some information that the reliability of our correction procedure is now much lower than in this than in this previous case, where here basically we were almost certain that we have successfully corrected the error. So this kind of errors, so if we measure the syndrome very close to the boundary, there is a quite likely possibility that our correction operation failed. And so while this information on its own cannot really help us, so we perform the most likely correction, and then we can also quantify mathematically how likely we have, what is the likelihood of failure in that correction. We will find that this information can be used on a higher level. So now let us consider a simple 4-qubit error correction code that has such 3 stabilizers. So now we consider a set of 4 qubits that are entangled in such a way that they are stabilized by these three stabilizers. So they are in a +1 eigenspace. So these operators. But for qubits, this is just a simple error detection code. So let's say I measure if my state was in the code in the code space of this code, and I measured Z1, Z2. I should get a value +1. But let's say I got a value -1, which tells me that there was an error. But I still have no information. I only know that there was an error, in this case an X flip, on either qubit 1 or 2. But I don't know on which qubit it happened, and I would need to guess. So that's why this 4-qubit code effectively is only an error detection code. But now if we consider the scenario where these 4 qubits are actually not qubits, but they are themselves GKP qubits, so I entangle 4 GKP qubits into the code words of such a 4-qubit code, then I can actually use this analog information. So let's say what happens is that I encode this state in those 2 codes, so in a GKP code, and then 4 GKP modes I entangle into this stabilizers, I entangle into code words of this code, and then I send it through this, let's say, lossy channel with loss probability gamma, apply this amplification to convert it to this random displacement. Then I apply this GKP correction as discussed on all the 4 qubits, all the 4 GKP qubits independently. And then this syndrome, not only do I apply this correction, but the syndrome outcomes I also forward to the next step, in which now I measure these stabilizers. And now let's say I here measure Z1, Z1, Z2, and I found that the eigenvalue is -1. So then I can use the analog information from the previous step, because I know that the reason why one of these qubits, 1 or 2, had an error was because I failed to correct that error on the GKP level. And on the GKP level, I failed to correct this error and effectively resulted in a root pi shift, which caused that logical level error on the higher level. So now I can use this error likelihood information to find out which of these 2 qubits, 1 or 2, is more likely to have that error. And this is the one that I will correct. So what that means is that through this concatenation, this 4-qubit code is no longer just a simple error detection code, but can, well, probabilistically, but with high probability, using this analog information, should be able to actually correct single qubit errors. And in some situations, can actually also correct 2-qubit errors. But to first order, we can say that we can now correct most of single qubit errors on the higher level.
You have 10 minutes.
Okay. And then we can do exactly the same with the 7-qubit code. So here, basically, this is a Steen code that has this larger number of stabilizers, and we do exactly the same procedure. And then we can find that this code can correct probabilistically even 2-qubit errors. So now, to provide some kind of intuition how this analog information and this code concatenation work, what is its performance? Let's say that we precisely do what I have just now described. So we encode the state in those 2 codes, send it through the channel, where effectively, if we have photon loss probability gamma, then our strategy of amplification followed by the pure loss channel effectively results with this Gaussian random displacement channel with standard deviation given by square root of gamma. And then we do this GKP correction and then the correction on the higher level. So what is the performance? So here we plot the logical error probability as a function of this loss gamma, where the logical error probability is the probability that after we have done the correction on both levels, we still end up on the second level with some logical flip, like an X, Z, or Y flip. And so we see that, and of course, the higher the loss probability, the higher the logical error probability. But we see that if we start with only this GKP encoding, we obtain this blue line. And then if we start concatenating the codes, we see that we can significantly push down this logical error probability. And another more interesting thing is that we can also see that this analog information is very useful. So if we consider a 7-qubit STIM code with analog information corresponding to this yellow line, then if we now decide not to use this analog information, then that means that we now use the STIM code to only correct single qubit errors, because if we don't use analog information, we cannot really correct 2-qubit errors. Then we see that the performance decreases, and we obtain the purple line, which basically is very similar, very closely overlaps with the red line. So I have already said that the simple error detection code for this 4-qubit code, 412 code, with analog information can correct single qubit errors, which is basically similar to what a 7-qubit code can correct without analog information. But if we add the analog information to the 7-qubit code, we can reduce the logical error even further. So this kind of shows that this concatenation method together with this analog information can give us a very significant performance boost. So now we have all these building blocks to put it into the repeater architecture, which basically we will say looks like this. So we have two types of repeaters. We have simple GKP repeaters that only perform this GKP error correction on the single GKP mode. So this mode can only store a single, this repeater can only store a single mode. And then this multi-qubit repeaters that can store large number, say 7 modes for the 7-qubit code or 4 modes for the 4-qubit code. And then after performing this operation of this, say 7 modes, it sends them sequentially through this chain of GKP repeaters. And if a given GKP repeater fails to correct an error or results in a logical error on a GKP level marked here with red, then the next, when all these qubits arrive to this multi-qubit repeater, this multi-qubit repeater should be able to detect and correct this error. So now let me show the results of the simulation. So we will see what kind of distances in kilometers we can achieve, for which the secret key would stay above, let's say, 1% of a secret bit per optical mode. And then we can also compare it with what is such, if we consider direct transmission with optimal devices and optimal encoding, we know this is a capacity of the pure loss channel, that the secret key will drop to 1% of a bit per optical mode at around 109 kilometers. So this is some kind of a reference. Okay, so if we use only the GKP encoding, our achievable distances look like this. So here we consider different value of this coupling efficiency and different value of this squeezing. And we color code different achievable distances. And we see that with GKP encoding alone, for most of these parameters, we actually cannot even reach 100 kilometers. If we consider concatenation with the 412 code, then we see that we can definitely achieve larger distances, and the region with distances above 1,000 kilometers is much larger. And concatenating with the 7-qubit code, we actually, for most parameters, we are able to achieve very large distances. Okay, so this was in terms of achievable distances, and then in the last 5 minutes, I will basically describe how we can optimally place such repeaters. So we define some cost function that tells us repeaters will be the blue line minus the green line. And the red line corresponds to what would be the optimal number of multi-qubit repeaters if we were only allowed to place this more powerful multi-qubit repeaters and not this cheaper GKP repeaters. So we see that considering a hybrid architecture that uses 2 types of repeaters enables us to significantly lower the amount of needed, this more costly repeaters at the expense of requiring some of this cheaper GKP repeaters. And the same we see here for the 713 code, where the 713 code multi-qubit repeaters are more powerful, so we need even less of this multi-qubit repeaters in this case. Okay, and the final plot is, so what is the value of this cost function actually? So here I described the optimal placement. Now for that optimal placement, we'll consider the cost function. So here we have 4 curves corresponding to a hybrid scheme for a 412 code and a hybrid scheme for the 713 code, and the corresponding schemes if we consider an architecture that is not hybrid but only uses this more powerful repeaters. And then we see 2 things. One is that the hybrid repeaters always allows us to save us resources with respect to the scheme that uses only multi-qubit repeaters, and that we can see by if we comparing the blue line, which corresponds to the hybrid scheme for the 412 code, with the red line. So the blue line for most distances stays below the red line, and similarly for the 7-qubit code, the orange line for most distances stays below the purple line. And secondly, we also see that for distances up to around, say, 2,000 kilometers, it's cheaper to use this 4-qubit code. And at some point, the 4-qubit code stops being able to perform well. And then the cheapest option is to switch to the orange line, which is the hybrid scheme based on the 713 code. Okay, so to conclude, I have described this concatenated coded repeater architecture that offers the possibility of long-distance quantum communication. And we see in particular that using this analog information and the 2 types of repeaters play key roles in enabling us to obtain very good performance versus cost trade-off of this scheme. Thank you very much. Okay,
thank you very much. And we have time for questions. There was one question from Sebastian Borówka before. He asked, what is the current experimentally implemented number of nodes in quantum repeaters in general? The question is about the present state of the art, the biggest advancements in quantum repeaters implementation.
Mm-hmm. So I think, of course, we have all these different technologies. So the error correction repeaters are definitely more of a future. So at the moment, we are more looking at these repeaters based on heralded entanglement generation that are considered at the very beginning. And this type of architecture is being now actively considered both in the Netherlands and through this Quantum Internet Alliance in Europe, and in China in the group of Jianwei Pan. But the problem is that at the moment, as far as I'm aware, these repeaters have. So if we define a repeater as something that can perform better than direct transmission, then it hasn't been yet demonstrated that performing entanglement swapping on a memory can actually allow us to do better. So this type of operations, as far as I know, have been performed, but the problem is that the quality of the operations and the storage has not been enough, such that, let's say, if we wanted to perform a quantum key distribution at the moment with the current parameters that we have in most devices, we would still perform better doing direct transmission than with this repeater because of the quality of the operations. I can also say that in Misha Lukin's group, there was an experiment, I think, last year that was very promising. So they have actually showed that for quantum key distribution, they could do better than direct transmission, but only assuming a very restricted set of attacks on the eavesdropper. So for full security, as far as I know, there hasn't been any experiment that overcomes direct transmission and that is based on use of quantum memories. Another story is that there are repeaters that are not scalable, that use only that are based only on photon interference, and there is a scheme called twin field quantum key distribution, and this scheme by people from information theory community is considered a repeater. It doesn't use any memory, so it's not scalable, but it is actually able to extend the communication distance by a factor of 2 with respect to direct transmission, and that has been demonstrated experimentally.
Okay, any other questions? Yeah,
I would have yes, I would have a question, but I'm just waiting for the others. So I understand that in the model of your model, Filip, you have this preparation of perfect delta function grid. Then it goes into the channel, which becomes this Gaussian noise, and then you amplify it, no? So I understand in your model, you still have some way of preparing this perfect delta function grid. So the question is how one would do it. And then my second question is just, I mean, I'm not asking for experimental implementations, just to get intuitions. But then you need to implement this secondary quantum error correction code on top after you amplify. Mm-hmm. So I understand you need to apply this Z1, Z2 operations on this grid, no? And I literally have no idea how to do a Z1, Z2 operation in this phase space. So, or maybe this is obvious.
Let me see. Okay, so so maybe let's start with the second question. So how one would do this, how we envision to do this GKP error correction is basically a similar Steam code error procedure in the same way as one would do for discrete codes, except that your qubits are now GKP qubits. So if you have a data qubit, you prepare an ancilla in a GKP. So this is for GKP error correction. Now later we will go to how to measure this higher level stabilizers. So you have this discrete, you have this data qubit, an ancilla that you prepare in a GKP plus state. You apply a continuous variable sum gate from the data qubit onto the ancilla, and then you measure the ancilla. And now you can think that because the ancilla itself was a periodic grid structure, doing homodyne detection. So here you do homodyne measurement. Doing a homodyne detection on this ancilla, you will get some number, yeah? Let's say Q0. But this Q0 doesn't collapse this data state because you don't know that, because both the data qubit was a periodic grid structure and the ancilla was a periodic grid structure. Okay. So somehow the periodicity of this ancilla masks whether the absolute value of this quadrature such that you don't collapse the data state, but you only read off from that value by how much the data mode has shifted, and then you apply this as a feedback, and you can correct. Is that clear?
Okay, I don't know how to do a control not on a two continuous variable system, but I trust.
Mm-hmm. So this is just a Gaussian operation given by. So your Hamiltonian will be just okay. So if you do a sum, this will be just.
Okay, it exists. I don't want to.
Yeah, so it's like P1. Like let's say if you want to do because here you want to displace Q quadrature of ancilla conditions on the value of the Q quadrature of data. So that would be so the displacement operator would be P. So you will have P on the ancilla, and you displace by the. So it will be Q data times P ancilla. So this will be your Hamiltonian, and then. Under such Hamiltonian, you can implement this operation. This will be a Gaussian operation. And then similarly, you can measure these higher level stabilizers, which basically works exactly the same. So if you want to measure Z1, Z2, you firstly apply this continuous variable sum gate from data 1 onto the ancilla, and then from data 2 onto the ancilla. And then you measure the ancilla. That will give you some continuous number from which you can post-process to get this discrete value of plus or minus 1. So that was regarding your second question, and you're coming back to your first question. So we assume that the GKP states don't have perfect delta functions, that they have this finite amount of squeezing, which so basically you can think of it as if as in an approximation, that you can think that we model them as perfect GKP states that have some random displacements due to finite amount of squeezing already.
But can you say simply how you prepare these states in experiment?
Okay, so so at the moment there have been two experiments, that have prepared such states. One of them was in the microwave domain, where so you need some nonlinearity. So this experiment at Yale was performed using a transmon qubit. So you use a transmon qubit as a source of nonlinearity, and then basically you can apply control gates from the transmon qubit onto a bosonic mode in a cavity, and then measure the transmon qubits, and depending on the outcome of the measurement on the transmon qubit, you apply some displacements on the bosonic mode, and in this way they were able to prepare a GKP state with squeezing, I think, of around 8 dB. And then there was a second implementation which was in vibrational modes, I think ETH Zurich, in vibrational modes of trapped ions. I don't remember exactly what was the procedure there, but so basically, as far as I know now, there hasn't been any experimental realization in the optical domain. One way of how one might consider going to the optical domain is either considering transduction from microwave to optical, or there are some proposals how one can generate this GKP states by fusing multiple cut states. So cut states are superpositions of two coherent states that already have some negativity in the Wigner function, require some nonlinearity, and there are some procedures how we can recursively try to fuse such cut states to obtain such a GKP state. But
okay, any other questions? I just want, okay, so if there are no questions, maybe just a short one. So how do you compare your scheme with other schemes, bosonic error correcting codes that protect from loss? So if you compare your scheme with like this bosonic error correcting codes that protect you from loss, what can you say?
So I think, so that's a good question. I think, so there has been a study done by shown that that the GKP code seems the most promising. So firstly, it's very easy here to use this analog information. So if I want to consider this concatenation of codes, for the GKP code, there is a very natural way of using this analog information. And another, there is a numerical evidence to show that the GKP code will be superior to other codes if one considers something what one would call an optimal decoding strategy. So here in this first step, we can consider this simple strategy that I said, that we do this loss channel followed by amplification. The former PhD students in the group of Liang Zhang has considered the scenario that we encode the state in the GKP code, and then we want to optimize over all possible encoding when we restrict the space to some n-photon space and run a semi-definite program. And it turns out that one can perform much better than this strategy here. That there effectively exists an achievable strategy that does much better than this. The problem is that because this is a result of semi-definite program, we only know that this is achievable, but we don't know what is the actual operation that one needs to do, because it's very difficult to decipher that from the choice state. So I think that's so maybe the reason why we chose the GKP state is not only this performance for this specific encoding strategy, but because there are also promising ways of improving the performance with improving the encoding strategy.
Okay.
But I'm not aware of such scenarios for other continuous variable codes.
Okay, thanks a lot, Filip, for this talk, and that's the end of our seminar. So thanks everybody for participation, and thanks, Filip.
Thank you.
Thank you.
Thanks.